to the 1.3 mole review. The extra practice that is not assigned but optional and recommended. I'm going to take at least 3 questions from these problems and put them on the quiz on Thursday, verbatim. So I would recommend you work through these. It'd be very good practice for anybody. All right, so with that aside, let's get started. So we've listed here 6 useful types of conversion factors depending on the situation. So we may come back to use some of these. And let's get started with question 1. So we've got a Canadian nickel, and that weighs 3.95 grams, which sounds like a bit much, actually. But my heuristic for how much a gram weighs is not that great, so maybe that's right. I looked that up on the internet. How much would a mole of nickels weigh? All right, so what's given? So I'm going to use a green highlighter, G green for given. So we know a nickel weighs 3.95 grams. And we know that we have a mole of nickels, so that's given as well. And what we're asked for is, maybe I'll use orange for required. So what's required? What's required is how much would a mole of nickels weigh? And that orange looks a little more like peach, but I'll get over it. All right, cool. Okay. So what's tricky is to always decide, well, what are we really beginning with in this question? What's constant property of our values and what is specific to our situation? Well, I would argue what's specific is that we have a mole of nickels, which is a lot of nickels. All right, so what I'm going to start with is a 1 mole of nickels. Not a mole of nickel, the atom, or the element, pardon me, a mole of the quantity, nickels, individual nickels, and there's going to be a mole of them, which means there's going to be quite a lot of them. All right. So I want to cancel out moles, and eventually I want to figure out how much they weigh. So first I'm going to figure out how many nickels is a mole of nickels. And so to do that, I would use the Avogadro's number. And what I'm counting with atoms is, instead of atoms rather, is going to be nickels in this case. So 6.02 times 10 to the 23 nickels is the same thing as 1 mole of nickels. And my moles of nickels cancel out. Now I don't actually know how much that weighs yet, so I still need to convert a nickel into a mass of some sort, and this many nickels into a mass, and so I know that 1 nickel weighs 3.95 grams, so I can make a conversion factor that says 3.95 grams is the same as 1 nickel. And nickels, again, cancel out. And so now I just get a straight conversion. Now, I think I might have made that harder than it needed to be. If it makes sense to you that if I wanted the weight of 10 nickels, I would multiply this by 10. If I wanted 100 nickels, I would multiply this by 100. If I want a mole of nickels, I would multiply this 3.95 by the number of nickels there are, which is a mole of them. So you might have gone that route. 6.02 times 23. And I end up with 2.38, rounding, times 10 to the 24 grams, which is pretty heavy. I think the mass of the Earth is something times 10 to the 24 kilograms. This is about 3 orders of magnitude smaller than the weight of the Earth. So it's pretty heavy. All right, moving on, question 2. All right, so what's given here? So we're given that we have a 100 ml sample of nitroglycerin. So it's given that we're talking about nitroglycerin. That might become useful later. And a 100 ml sample has 0.705 moles of nitroglycerin. And the question is asking or requiring how many nitroglycerin molecules. Okay. So let's take a look here. Well, if I want to find out the number of molecules, I've got a volume and I've got a number of moles. I'm actually given two things to begin with. Now, can I convert from volume into a number of molecules? Maybe. But to do that, I might need to know something else. I might need to know the density or something. And actually, I'd have to convert into moles anyway, which I'm already given. So I'm actually going to start with moles. Moles of nitroglycerin. It's going to be a pain to write, so I'm just going to write moles. And what am I going to convert that to? I'm going to convert it into molecules. And so I can use Avogadro's number to convert moles into numbers of particles, atoms, or molecules. And so I can say 1 mole of nitroglycerin is equivalent to 6.02 times 10 to the 23 molecules of nitroglycerin. And that's it. Moles cancel, and we're done. All right, so what do we get? We got 0.705, and we multiply that by 6.02 times 10 to the 23, and I get 4 point, how many sig figs I should get? 3 sig figs to 4 times 10 to the 23 molecules. Okay. Moving on. All right, so we've got global internet traffic for 2015 was, okay, that's a really big number of bytes. If I wanted to say it, it's, okay, so it's millions, billions, trillions, quadrillions, pentillion, 72 pentillion, 521 quadrillion bytes. The question is how many moles of bytes? Okay, so if I want to convert a number of something into moles, again, I can use Avogadro's number. All right, so what's given? We have this many bytes, and we're asked for how many moles of bytes. All right, so to do this, well, first I might, rather than write this out, to convert this into scientific notation, so I'm going to take this decimal and move it over 1, 2, 3. Maybe I'll zoom in a little bit. And focus. All right, so move it over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So I could say that's really 7.2521 times 10 to the 19 bytes. And I can say, well, 1 mole is equivalent to 6.02 times 10 to the 23 bytes. Bytes end up canceling. And so then that's just a division question. Okay, so I get 7.2521, 19, and I'm going to divide by Avogadro's number. And I end up, I have 3 sig figs in Avogadro's number. Had I used more sig figs from Avogadro's number, which I happen to know and is measured, I could include them. But that's actually not that small a number of moles. I can think about that as a quantity. I could actually write that out. It'd be 0.0001201, 1, 2, 3, 4, yeah, moles. All right. I think I'm going to zoom out just a bit so I can at least see the whole page. There we go. All right, moving on to question 4. Question 4 reads that a large blue whale has 1.62 times 10 to the negative 10 moles of cells. And the question is, how many cells is this? How many cells? So we need to convert a number of moles into an actual deal-withable number. Okay, we can do that. So I can say, okay, for question 4, I have 1.62 times 10 to the negative 10 moles. And I want to convert that into a number of cells. So first I need to cancel out moles diagonally. And I want cells as my new unit. Well, how many cells is a mole of cells? Well, same number of things as anything is of a mole. Is 6.02 times 10 to the 23 cells is 1 mole. So my moles end up canceling diagonally. And I've found out the number of cells. I just need to punch that into a calculator now. 1.62 times 10 to the negative 10. And I'm going to multiply that by 6.02 times 10 to the 23. And I get 9.75 times 10 to the negative, pardon me, to the positive 13 cells, which is a healthy number of cells for any being. Moving on. All right, so question 5. I've got an old cathode ray tube television, and it has an electron gun that fires 3 million electrons a second. Question is, how many moles of electrons would be fired if it was left on for a year? All right, so what's given? We're given that we've left it on for a year, so that's given. And we're given that we have 3 million electrons every second. And we're required to answer the question of how many moles of electrons this is. All right, so what are we starting with in this case? Well, this is a constant state of any television, but what we're beginning with is this idea that, well, in this specific situation, we're leaving it on for a year. If we left it on for a day, we get a different value. So that's going to be our initial value. I'm going to start with 1 year. 1 year. Okay, so to begin with, I'm going to convert that into days. Because eventually I need to turn it into a number of seconds. If I can turn it into a number of seconds, I can convert it into a number of electrons. Because if I know how many seconds there are, I can figure out how many electrons there's been. So, but first, I don't know how many seconds are in a year, but I know how many days are in a year. I know 365 days are in 1 year. And I know there are 24 hours in a day, so I can convert days, 1 day, into 24 hours. And I happen to know there are 30, let's do this in 2 steps. I can say there's 60 minutes in an hour. And there are 60 seconds in 1 minute. And now I've converted my values into seconds. My years cancel out, my days cancel out, my hours cancel out, my minutes cancel out. And I'm going to convert that into a number of electrons. And I get 3 million electrons in a second. So I'm going to abbreviate that as 3 times 10 to the 6 electrons. That's 3 million. In 1 second. And then I need to convert that into moles. So lastly, I could say, okay, well, 1 mole is the same thing as 6.02 times 10 to the 23 seconds. That's a mole of seconds. Oh, now that, mole of electrons, sorry. Yikes. And so that's why dimensional analysis helps us. We can end up noticing if we're making a mistake. Electrons end up canceling out, seconds. And so now we've converted a year into a mole, some number of moles of electrons. All right, so let's find out what kind of number we've got here. I'm not sure if this is big or small. Number of moles. 365 times 24 times 60 times 60 times 3 million. All right, and I'll divide all that by 6.02 to the power of 23. And I still get an astonishingly small number of moles, 300 million electrons every second for a year. It does not even make it to a single mole of electrons. That's how big a mole is. So I can say that could round to, well, technically I only had 1 sig fig from that 3 million, so I'm going to round that to 2 times 10 to the negative 10 moles of electrons. All right, moving on. Question 6. Current best estimate for the number of ants in the world is 10,000 trillion, or 1 times 10 to the 6 ants. Those are given values. And the question is, how many moles of ants? And we're also required to express this in expanded form and scientific notation. So that's just a good thing to be able to do when we're tasked to. All right, so we should start with the thing we're given. We're only given one thing here, which is we have 1.0 times 10 to the 16 ants. And we're going to convert that into moles. So I know that 6.02 times 10 to the 23 ants is the same thing as 1 mole of ants. And so ants cancel out. And I can say, okay, well, if I've got 1 times 10 to the negative 16 ants. Oh, no, it's the positive. I don't know what I'm thinking. And then I'll divide by 6.02, divide by 23. I get a small number of ants. What do I get? I get 1.7 times 10 to the negative 8 moles of ants. Oops. And if I want to express that in expanded form, I'll take that decimal, I'll move it over once, twice, 3, 4, 5, 6, 7, 8 times. Put a little decimal there, and I'll add zeros in all those places. Moles of ants. Because I think sometimes it's important to recognize how big a scientific notation number is and bring it back to earth a little bit. All right. So those are the mole questions. So there's going to be one question like that on the quiz on Thursday. One question just involving moles, but not really involving molar mass or anything. We'll move on to question 7. So question 7 gives us a value, a weight of 109.13 grams for the world's largest cut diamond. And we're also given that diamond is made of carbon, if you didn't know that. The question asks for us for how many moles of carbon atoms. All right. Well, to do that, we will start, I think, well, we're given a mass. So we'll start by writing down question 7. We've got 109.13 grams of a diamond. And we need to somehow turn it into a number of atoms. Now, if we're not sure how to do that, because I don't know of a conversion factor that turns things from grams into atoms directly. So if we're ever not sure, we should probably aim to get things into moles first. Now, do I know something that turns things from grams into moles? I do, and if I look at the top of the front page here, I can see that to go from mass, convert it from mass to moles, I can use the molar mass. And I've got an example of zinc here. 0 grams per molar, moles per gram. But I want to use carbon in this case. So let's find the molar mass of carbon. So I'm going to abbreviate that mm of carbon is, and I look on my periodic table, I find carbon here, and it is 12.0 grams for a mole of carbon. Every mole. All right. So to convert these grams into moles, I can say, well, grams are going to live on the bottom, so they cancel out. So it's 12.0 grams for every 1 mole of carbon. Great. Now, that isn't quite what I was asked. I was asked, oh no, it is what I was asked. So I was asked, oh, I got a little mixed up. I thought we were asked for the number of atoms. We're actually just asked for the number of moles. So actually we're done here. We've canceled out grams and we've got moles. So actually all we need to do is do a division here. It says 109.13, oops, clear, 109.13 grams divided by 12 gives us 9.09 moles. All right. Moving on, we'll look at the Fat Man, the one of the 2 nuclear bombs that were used in an attack by the United States on Japan. And it contained 6.2 kilograms of plutonium. And the question asks us for, or requires, how many plutonium atoms is this? All right. So, for question 8, well, we're only given one quantity at 6.2 kilograms. Now, in order to deal with that, I'm going to need to turn it into moles. So I know I can use a molar mass of plutonium, just like we did in question 7, to convert mass into a number of moles. However, I have kilograms, and molar mass usually converts grams into moles. So what I can first do is turn that into grams. I know that there are 1,000 grams in 1 kilogram. And so they they cancel diagonally. All right, and next I can convert grams into moles. Now, I look on my periodic table here for plutonium, and I see that plutonium has a molar mass of 244 grams per mole. And so I can say that 244 grams of plutonium is equivalent to 1 mole of plutonium. And that's not quite what we're after. We're after how many atoms that is. So I can convert moles into a number of atoms by using the Avogadro's number, the mole itself, to convert from atoms to moles. Okay, so lastly, I can say, okay, well, then if I want 1 mole to cancel out, and I know that 6.02 times 10 to the 23 atoms is the same thing as a mole. So moles cancel, grams cancel, it all cancels, and we end up with just punching this into a calculator. So what do we got? 6.2 times 1,000 divided by 244 times Avogadro's number. And I get, well, how many sig figs? That gives me 3 sig figs from the molar mass of plutonium. And so it's 1.53 times 10 to the 25 atoms of plutonium. I think this Pu is the atomic symbol. All right, moving on to question 9. So Mowat's got a platinum grill, and it contains a certain number of platinum atoms. And the question is, well, what is its mass? Well, if we look at the last question, we started with mass, and we ended up going to atoms. Here, we're given a number of atoms, and we're asked to give a mass. So we're going to end up going backwards here. So we can imagine undoing everything we just did. And let's just take a look at how that looks here. So we'll begin with this one thing we're given, which is 1.410 times 10 to the 23 platinum atoms. And I don't know how to turn that into mass directly, but I know that I generally want to get things into moles, because that's usually the trick for any sort of conversion in chemistry. So I'll start there. I can convert a number of atoms into a number of moles, because I know 6.02 times 10 to the 23 atoms is equivalent to 1 mole of platinum. Okay, and now I can convert a mole into the weight of Mowat's platinum grill. And I can do that using the molar mass. The molar mass of platinum is 195.1 grams for every mole. And so I can say, well, I want moles to cancel out, so I'll put the mole down here. And I can put the 195.1 grams up here. So moles cancel, atoms cancel. And now I have a number of grams for Mowat's Platinum Grill. All right, so what do we got? 1.41 power of 23 divided by 6.02 to the power of 23. And that's all multiplied by the molar mass. And it gives us 45.7 grams. And that's how much Mowat's Platinum Grill weighs. Moving on. Okay. So we have the nutrition facts for some Doritos. Okay. And we're asked how many atoms of sodium are in a single serving of Doritos. Okay. So sodium, let's see, it's a metal. And now in Doritos, sodium is going to be found in its ionic form, like in salt, sodium chloride. And we can see that there are 210 milligrams of sodium. So that's what's given here, 210 milligrams of sodium. And we're asked a question of how many atoms. So this is quite similar to the Fat Man question. We're given a mass, and we're asked how many atoms. So we're going to find that these types of questions are often quite repetitive. So I'll write down, I guess, what I'm given here. I'm given 210 milligrams of sodium. And I think before I get started, I should probably convert milligrams into grams. I know that 1 gram is 1,000 milligrams, just like a liter is 1,000 milliliters. Okay, so then I can convert the number of grams of sodium. Well, I don't know, where should I go from here? Generally speaking, I want to turn things into moles if I can. So to convert from moles into mass, I can see that molar mass will allow us to do that. All right, so the molar mass of sodium. So I look on my periodic table. I see that the molar mass of sodium is 23.0 grams for every mole of sodium. So I want grams to cancel out, so I'll put them down here. 0.0 grams for every 1 mole of sodium. And we're not quite done because we're asked how many atoms. So lastly, we need to cancel out that 1 mole. And we can use Avogadro's number because I know how many atoms there are in a single mole. There are 6.02 times 10 to the 23 atoms. And I'll just check that everything cancels out diagonally, and they do. Great. And so then I can just say, okay, I've got 210 times 1 times 1. Oops, times 6.02 times 10 to the 23. And I'll divide that by 1,000. And I'll divide it by 23. And I get 5 point, how many sig figs? 210 is, I guess, 2 sig figs, so I should say it's 5.5 times 10 to the 21 atoms of sodium in a single serving of chips. All right. So moving on, we've got Michelangelo's David, and that's a marble, which is actually just calcium carbonate, which is a mineral that's made by compressed shells of dead shellfish in the oceans, all accumulated, which is pretty fascinating to me. All right, so what are we given here? We're told he's 5.7 meters tall. We'll see if that's useful. We know that it's calcium carbonate. That might be useful. And that overall it weighs 6,100 kilograms. The question is how many atoms there are. All right, so, so how many atoms? All right. So, what do you think? Well, let's take a look. 5.7 meters tall. Is that relevant? Does it matter how tall it is? What if it was like made really skinny and really tall? Would that change how many atoms are in the structure? No, it wouldn't. This is irrelevant. And in real life, we can expect some information to be relevant and some information to be irrelevant, and our job is often to choose what we think is the most pertinent quantity. So actually, we're just converting a mass into a number of atoms, very similar to what we just did with Doritos. All right. So what do we have here? We have Michelangelo's mass is pretty heavy. It's like 6 tons. 100 kilograms. All right. And, well, I have seen I need to turn things into grams, so I'm going to do that first. So I know 1 gram. Oh, no. What do I know? I know 1 kilogram. It's the same as 1,000 grams. Okay. And then I should probably turn the number of grams that is into some number of moles of calcium carbonate. To do that, I need the molar mass of calcium carbonate. Okay, so for the molar mass of calcium carbonate, I should probably find that we have 1 calcium, which has a mass of 40.1 grams per mole. I know I have 1 carbon in a calcium carbonate molecule, which is 12.0 grams for every mole. And I have 3 oxygens. 3 oxygens, they're 16.0 grams each, so I multiply that by 3. I get 48. Let's write that differently. Let's say it's 3 times 16.0 grams per mole. If I add all that together, plus 12 plus 3 times 16, I get 100.1 grams for every mole. Okay. So I want grams to cancel out, so I'll put them down here, and moles up here. So I have 100.1 grams for every 1 mole. You know what? I think I'm going to write it over here so I can indicate this is calcium carbonate. And there's a reason for that, because I'm actually asked how many oxygen atoms there are. And I know that, well, you know what? Let's first turn this into molecules of calcium carbonate, and then I'll deal with the oxygen afterwards. Okay, so to turn something from a number of moles to a number of molecules, well, I need Avogadro's number. 1 mole is equivalent to 6.02 times 10 to the 23 molecules of calcium carbonate. And I find it's useful, sorry for the mess here, guys. I find it's useful to write out the substance I'm dealing with when it looks like I'm going to be converting from one substance, calcium carbonate, as the question asks, calcium carbonate into oxygen. So I'm going to be changing the substance. So sometimes it's useful to keep track of which substance I'm talking about. All right, and so lastly, I would say, okay, for every 1 molecule of calcium carbonate, I'm going to abbreviate that molec, calcium carbonate, I have 3 oxygen atoms. Oxygen. Okay, now molecules of calcium carbonate cancel, moles of calcium carbonate cancel, grams cancel, kilograms cancel, and we're just left with a long thing to multiply together. And what do I get? 6,100 times 1,000 times 6 times 10 to the 23 times 3, and then I divide that all by 100.1. And it turns out there's quite a few oxygen atoms in Michelangelo's David. How many sig figs should I get? I guess I get 2 from the mass, 6,100 kilograms. So it would be 1.1 times 10 to the 29 oxygen atoms. I'll put that in a little box. Okay. Let's move on. Question 12. The transatlantic telegraph cable. I love that transatlantic cables exist. It's one of my favorite things we've done as a society. Now, the first telegraph cable from the 1800s was 2,600 kilometers long. It carried 7 copper wires, and each wire weighed 26 kilograms for every kilometer. Okay, so let's start with 12A. How many kilograms of copper were used? Okay, so to answer that, I'm going to say, okay, well, what do I begin with? Well, I know that it was 2,600 kilometers long. So I know that for sure. 2,600 kilometers. All right. And that's the distance. All right, and I know that... what should I do next? I'm actually just thinking, planning myself here. Should I deal with the fact that there are 7 wires for every kilometer? But the wires and kilometers don't quite cancel out. I think what I'm going to do is I'm going to calculate the amount per wire. And then I'll say, well, and there are 7 wires, so I'll multiply that by 7. Okay, so that's what I'll do. All right, so I've got 2,600 kilometers. All right, and I know that each wire is 26 kilograms. 26 kilograms per 1 kilometer of wire. Of wire. Okay, so I'll fuzz with it there. All right. So make those a little bit more clearly X'd out. Okay. And I know there are... You know what? I hate that. Let's just get rid of that. I don't know if there's a really elegant way to do this all in a conversion factor, or at least I can't think of one. I know intuitively that whatever number I get here, I'm going to multiply by 7. So that's actually just what I'm going to do. So this is going to tell me the amount for a single wire, and I'm going to multiply that by 7. It says 2,600, kilometers cancel out, times 26. That'll give us 67,600 kilograms per wire. And I'm going to multiply that by 7. And that will give me 473,200. But I only have 2 sig figs, so I should probably round that. And so that'll be 4.8 times 10 to the decimal place once, twice, 3, 4, 5 times kilograms. That's a lot of copper. I think you'll agree. It's almost it's about 500,000 kilograms of copper. Transatlantic cables, transoceanic cables, are massive. It is an amazing feat. All right. Next, we want to know, okay, well, if that's how much it weighs, how many moles of copper were there? Okay, and that's actually not so bad once we have this. We can convert mass into moles. That's something we've done before. So, but before we do that, we first need to turn it into grams. Okay. So we'll say, okay, so that is, I know 1,000 grams is in a kilogram. And I can look up the molar mass of copper to convert mass into moles. I know the grams cancel out. I have moles here. And I can see that the molar mass of copper is 63.5. 63.5 grams for every 1 mole. And so I can take that number, multiply it by 1,000. I'm actually going to keep that number in my calculator, and just because that's going to be a more precise value. And then I'll divide it by 63.5. And so I end up, again, I should have 2 sig figs. So that's 7.5 times 10 to the, wait, that's a lot. Oh, it is a lot, I guess. It's a lot of moles because it's a lot of copper. 1, 2, 3, so that's 7.5 million. 7.5 times 10 to the 6 copper moles. All right. And how many atoms? Okay, well, that's going to be a tremendous number. All right, so I'm going to say, okay, I'll start with that value, 7.5 times 10 to the 6 moles of copper. And I can convert that into atoms using Avogadro's number, 6.02 times 10 to the 23 atoms for every 1 mole of copper. I'll multiply this by 6.02 to the 23. I get 4.5 times 10 to the 30 atoms of copper. Okay. Let's call that video there.